Hello and welcome to Lesson 9-2, Square Root and Quadratic Functions. We're going to continue working on inverses. We're going to graph and write the inverse of a square root function and find the inverse relations of quadratic functions. So all functions have an inverse relation, but the relation may or may not be a function. We've already talked about this. Okay, so recall that a relation is a set of ordered pairs that may or may not be defined by a rule. Not all relations are functions, but all functions are relations. Okay. So we're going to use the quadratic function g, graphed below, to graph the inverse of g. So to do that, what I'm going to want to do, really, I don't have the equation, but I could just simply switch the x and y in the ordered pairs. So since I have an ordered pair at 0, 4, I should, on the original graph, I should have one at 4, 0 on the inverse graph. And since it looks like I have an ordered pair here at 2, 8, and one here at negative 2, 8, those are two more ordered pairs, I could switch the x and y's. So I have 8, 2, and 8, negative 2. And that will give me enough to get the inverse relation. Okay, so now the question for part B says, is the inverse of g a function? Okay, and we would say that no, the inverse is not a function. Okay. We have many x values, many input values that have two output values. So we could say no, actually most of the x values have two y values. Okay. And what characteristic of the graph of a function can you use to determine whether its inverse relation is a function? So from the original function, we knew that that was a function because it passes the vertical line test. Okay, well, if we were to actually try a horizontal line test, and we would see that it does not pass the horizontal line test, it does hit in more than one spot horizontally, that means that its inverse would not be a function. So if the original function has, two x values, okay, for at least one y value, like we see in the original function, then its inverse will not be a function. So you learned about the vertical line test before. We can use the horizontal line test now to help us determine if an inverse is going to be a function without even graphing it. All right, so part D says, give the domain and range of the inverse relation in part A. Okay, so the domain and range of the inverse relation. So the domain looks like all the x's start at 4. So our domain are going to be all of our x's greater than equal to 4, or we'll say from 4 to infinity in the interval notation. Our range, however, is going to be all real numbers, or we could say all values of y. Okay. So on the next page we have an example A, and it says they give us a quadratic function. They want us to find the inverse and determine whether the inverse is a function algebraically. So we're going to try that now with the try these A. It says find the inverse of this function and then state whether or not that inverse is a function. Okay, so I'll work on that on the side here. Okay, so for part A, we have a function f of x, I'll call it y, equals negative x to the 1/2 power, which is the same as y equals negative times the square root of x. So I would need to switch x and y. So I'll put x here equals negative square root of y. Then we'll have to divide both sides by negative. Okay, so -1 and -1. So I have negative x equals the square root of y. And now we can square both sides. We get y equals x squared. Okay. So the inverse, f inverse of x, is x squared. That's a quadratic. And the quadratic is a function. We know the quadratic. It's a parabola. We know that that is a function. So say yes. So the inverse of the square root function was a quadratic, and it is a function. Okay. But in part B, we're going to work backwards now. In part B, it says find the inverse of a quadratic function. So if I have y equals x minus 5 quantity squared, and I switch x and y, so I have x equals y minus 5 quantity squared. I'll need to take the square root of both sides. Okay. And when you take the square root of both sides, remember you get a plus or minus. So I have plus or minus the root of x equals y minus 5. If I add 5 to both sides, I get 5 plus or minus the square root of x equals y, which is, of course, our f inverse, or our g inverse in this case. So g inverse of x is 5 plus or minus the square root of x. Now, this is a square root function. And a square root function, if we have the plus and the minus with it, well, then it's not a function anymore. So I shouldn't call it a square root equation. It's not going to be a function if we use the plus minus. So we'll have to restrict the domain in that case. So we say not a function. Okay, so go down here towards the bottom where it says, remember that it's possible to restrict the domain of a function so that its inverse will also be a function. So consider the graph of g of x equals x squared plus 4. Okay. Okay. And its inverse from item 1. Imagine covering the right side of the graph and drawing the inverse. So if we covered the right side of the graph, we would only have the side with the negative values of x for our domain. Okay, so that means the domain of g ends up being restricted to all the x's less than or equal to 0. So that means the inverse of g will be a function with a domain of x greater than equal to 4 and a range of y greater than equal to 0. So if we were to just graph those ordered pairs, so instead of 0, 4, we would of course have 4, 0. And then negative 1, it looks like we're up at 5. Well, instead we'll be at 5, negative 1. Okay. And then I see another ordered pair at negative 2, 8. Well, we would be at 8, negative 2. We would just have this part of the graph. So if we can restrict the domain to be x's, all the x's greater than equal to 4, and our range as just being all the y's that are less than or equal to 0, then we have an inverse that is also a function. Okay, we have a math tip over here that's definitely worth reading. We say the range of the inverse of a function is the same as the domain of the original function. You can use this fact to determine whether the inverse of a restricted quadratic function will be the top half or the bottom half of the inverse relation. Okay. So here we restricted our domain to be x is greater than equal to 4. Okay. We also could, however, restrict our domain in the original function to be all the x's are great. They were all less than or equal to 0. We could make them all be greater than or equal to 0 and graph the other half. We could graph them like the top half of the inverse function as well. We just chose to graph the bottom half of the inverse function. So we could do it that way as well. All right, so in this check your understanding box, it's kind of good for us to do here just so you understand where and when we have to actually restrict the domain. So it's a state whether the domain of each of the following functions must be restricted to ensure the inverse is a function. So we think about who the inverse is. If we have a square root function, remember the inverse is a quadratic. So we do not need to restrict a domain for a quadratic. Quadratics all pass the vertical line test. Okay, Okay. Number 6 is also a square root function. It's written with the 1/2 power. Again, the inverse would be a quadratic, so we don't have to restrict. But when your original function is a quadratic, you will have to square root both sides of the equation eventually, and therefore we will have a restricted domain. So in this case, we will have to have a restricted domain. So we would want to restrict the domain. This is a quadratic that would be shifted to the right the right 5. And so we would have to pick either all the x's on one side, so greater than equal to 5, or we could restrict it to all the x's that are less than or equal to 5. We would have to pick one or the other. Now, in number 8, for this one doesn't have, we don't have the quadratic in a form where we know the transformation or the vertex, but we do have a vertex formula that we learned with quadratics. Do you remember x equals negative b divided by 2a? So if we find the vertex, or even just the x value of the vertex, we know that's negative 6 divided by 2 times 1, which is negative 6 over 2, which is negative 3. So the vertex is negative 3 something. We could figure that out. But in this case, it's actually negative 3, 0. That's where it's going to be. This graph has been shifted to the left 3 units. And so all of our domain for our inverse function is going to have to be restricted to either greater than equal to or less than equal to negative 3. So either greater than equal to negative 3 or less than equal to negative 3, but not both. All right, a function is defined as 1-to-1. I haven't used that yet, but we talked about the horizontal line test. If for each number in the range of the function, there is exactly one number from the domain. If f of x is a 1-to-1 function, it'll pass both the vertical and the horizontal line test. So from item 1, the question is item 1 a 1-to-1 function? And we've already looked at that. We saw that when we drew a horizontal line, it did not pass. It definitely passes the vertical line test. It does not pass the horizontal line test. So it is not a 1-to-1 test. It's not a 1-to-1 function. It does not pass both vertical and horizontal line test. Okay. So a function whose inverse is a relation is 1-to-1. If we're talking about a function whose inverse relation is also a function, if we know that it will be considered 1-to-1. Okay, so let's talk about a couple of functions here that we know. It says determine whether each type of function will always, sometimes, or never have an inverse that is a function, assuming the domain of the function has not been restricted. So for linear functions will always have their inverses also being function. Okay, always, as long as the slope is not equal to 0. That's a tough one. So except when slope is not equal, when I should say except when the slope is equal to 0. So because then you actually get a vertical line. But for linear functions, their inverses are always going to be functions. Quadratics, well, we'll have to always restrict the domain. Quadratics always bend on their side, and then we have to restrict the domain. So their inverses are never functions until we restrict, because they look like this. Square root functions are always, because square root functions look like this, and they pass both the vertical and the horizontal line test, so that's going to be always. Okay, so I kind of feel like 11 should really be a sometimes answer, but they listed it as always, except for when m is not equal to 0, except for when m is equal to 0. Okay. Next page, we have the practice. So that's it. We're good to go. You guys will work on this for your assignment, and we'll also do some of these in class. Have a great